Good morning, everyone. I'm going to present today on some possible research opportunities at Corpus Christi. First, going to give you a little bit of an introduction to what we do, kind of a little bit of the history of the NWS for those of you who aren't familiar, but some of you that have a background in meteorology may already know some of this stuff, but I figured it'd be good to share. So the NWS has a fairly long history. Originally, it was called the Weather Bureau, which was founded in 1890. Um, and really, meteorology as a scientific profession began to really kind of blossom in the late 19th century to early 20th century, where you have things like the American Meteorological Society, or AMS, form. The Hurricane Warning Service, which would eventually become the National Hurricane Center, was formed in 1935. I think just before, actually, oddly enough, the most intense hurricane to hit the United States, the Labor Day storm in the Florida Keys. Some other big milestones include the first balloon sounding to sample the upper atmosphere, made in 1937. In 1959, there was the development of this strange-looking radar system you see on the right, which was called the WSR 57. Which would actually be the main radar used for almost over 20 years. And then finally, in 1970, the establishment of the National Oceanic Atmospheric Administration, and then the previously known Weather Bureau became known as the National Weather Service, and it was folded into the National Oceanic and Atmospheric Administration at that time. And then in somewhat more recent history, a big change occurred in the late 80s to early 90s. And this is sometimes referred to as the modernization period of the NWS. And there were many new kind of inventions in this time: the automated surface observing system, the ASOS, the upgrading of the radar system to the current radar system, which is called NEXRAD, or the WSR 88D. Although comically, the fact that it is 88 in the name lets you know that our current radar system, a lot of the hardware was designed in the 80s. So getting a little long in the tooth, but there have been some upgrades, namely the dual pole upgrade, which I don't have here, but it was in the mid 2010s. And then this AWIPS, this computing system, which you see an example of a workstation on the bottom right there. Which basically is how we look at a lot of the data, how we issue warnings, how we issue a lot of routine forecasts in the Weather Service offices today, which we'll go a little more in depth about that in the slides that are coming up. And then also it created the kind of NWS forecast office configuration or structure that still exists to this day. And so what is that structure? So at a base level, there was 122 weather forecast offices, also known as WFOs, which I'll kind of refer to interchangeably using the acronym or the actual word. As you can see, there's lots of them. There's some that aren't even listed, like Honolulu and Guam, San Juan, Puerto Rico, and then 3 offices in Alaska as well. So that each of these offices have the area of responsibility that's highlighted for usually a variety of counties and things like that. There's also 10 national centers: the Aviation Center in Kansas City, the Storm Prediction Center, SPC, in Norman, Oklahoma, Space Weather Center in Boulder, Hurricane Center in Miami, Climate Weather Prediction, and a lot of modeling centers in mostly College Park, Maryland. And then finally, there's the Tsunami Warning Center, which is in Palmer, Alaska. There's actually a second tsunami warning center, the Pacific one, that's actually in Honolulu, on Pearl Harbor, of all places. And then, so like I said, there's the structure that you have these local offices. And for example, just like narrowing into Texas, these are all the different offices that have responsibility for parts of Texas. So Texas in particular has the most offices of any state in the country, I think by a large margin. I think California is the only other state that has even a comparable number of offices. Obviously, we'll go into more details about our office, which covers this region of South Texas. You can see basically the coastal bend, the so-called brush country, and part of the Rio Grande Valley or Rio Grande Plains are covered by our area. One of the reasons why, you may ask, why is this collection, this patchwork of offices? A big reason are two things. The upper air sites where balloons are launched, they kind of want to be spatially representative, so you got good sampling of the atmosphere. And this figure on the right shows the upper air sounding sites for the U.S. So you see that corresponds to a lot of these offices. There are some offices that don't launch balloons. Houston and Austin, San Antonio are two examples that are near us that don't actually launch balloons. But this is a big reason. The second reason is that radar network coverage. As some of you may know, as a radar beam travels away from the radar due to the curvature of the Earth, the radar beam is getting higher and higher in a typical day, at least in typical atmospheric conditions. So the result is if you get really far from the radar, you start sampling well above where most of the clouds and precipitation are, and the data isn't particularly useful. So your goal is not to have huge gaps between radars, so you keep that low-level sampling. And this was really kind of the big focus of why the offices are where they are. You do see that there are even some gaps, which are kind of these white areas on the map where there isn't any radar coverage below 10,000 feet in Utah, parts of the Mountain West. So even with this dense network of offices, and each office usually has responsibility for one and sometimes two radars for some of the bigger offices. Even with this amount of offices, there are still some areas in the Intermountain West that are not sampled very well with radar. But outside of the Intermountain West, there's pretty good coverage everywhere, with some notable exceptions in parts of, like, for example, Northeast Louisiana, Southern Arkansas. There's a bit of a gap. So there are some negatives. So at a local office, if you're fully staffed, you have approximately 20 employees. Some of you may know we're a federal government agency, so currently most offices are not fully staffed, and probably won't be in the near future. But ideally, you have this kind of configuration of staffing. A meteorologist in charge is kind of the boss of the office. You have an administrative assistant, usually in charge of like the office budget, making sure that there are supplies and things like that. The warning coordination meteorologist, who's mostly going to be focused on making sure, meeting with partners, meeting with emergency managers, making sure the office is adequately, basically on the outreach side of things. The science and operations officer, which is my current position, which is basically make sure the staff is trained, making sure the latest developments coming from academia and research are making it into the office, and make sure everyone knows how to use these new and emerging technologies. The information technology officer is a lot of the software side of the office, making sure all our computer systems stay accurate and up to date. Although often my position also will have to help with that. Electronic systems analyst. This person usually helps with making sure that the hardware and equipment, observation systems, radar, even computing from a hardware, all the servers and stuff are in working order. Observation program leader, this position is usually in charge of making sure things like the balloon launches, the co-op observer program and such are in working order. This position, granted, is in the process of being phased out. There are 5 lead forecasters who are usually in charge of working on a forecast shift. They make the decisions usually on watches and warnings that will be issued. General forecasters, they're kind of, or meteorologists, are a little bit below leads. They're usually doing a lot of the work or the forecasting work, but they often will technically not have the final say in what goes out. And then electronic technicians to help with the equipment. This is a picture of the office, I believe, during Hurricane Beryl, so you can get a general idea of how the ops floor looks. This is more people than are certainly usually on the ops floor at a given time. Like right now, there'd be about 2 to 3. But for big events, there certainly can be up to 10, 11 people out here doing a variety of tasks. So like I said, as you saw from that bigger map earlier, this is our region of coverage. All the counties listed here. A few different, somewhat distinct geographic regions, from the more arid Rio Grande Plains and brush country out west to the Victoria Crossroads region, the coastal bend, which obviously is a little more humid subtropical. And our overall mission is provide weather, water, and climate data, forecast warnings, and impact-based decision support services for the protection of life and property and the enhancement of the national economy. The enhancement of the national economy part was actually added very late when we joined NOAA because we're in the Department of Commerce. So they felt that since we were not going to be in like the Department of the Interior, which was originally where the Weather Bureau was, that it made sense to add that statement as well. And these are some of our probably our core duties, I would say, are these bullet points here. We'll go kind of more detail about each one of these in a second. So one of the biggest things we do is we monitor radar and issue your typical severe tornado warnings. One of our biggest things that we have responsibility for. And so some of these alerts will go out through a variety of means. There's what's known as the WIA, which is the Wireless Emergency Alert System, which is for the most serious stuff. So your hurricane warnings, your tornado warnings, your flash flood emergencies, your very strong severe warnings with like baseball-sized hail, 80, 90-mile-an-hour winds. Those will actually go out to phones. There's the EAS, which is the Emergency Alert System. Most of you know that from when you're watching TV. You're watching, say, a football game or something, and then all of a sudden it starts scrolling on the bottom of the screen that there's a severe thunderstorm warning, etc. That's the EAS. That goes out for more warnings than the WIA. And then there are other things. I mean, we do automated social media tweets that go out, and then things like that as well. And then we also do a lot of hydrology stuff, which is your kind of more your flood watches. There's a variety of products. There's the flash flood warning. I won't go into detail of like what all these are. The river flood warning. There's river forecast itself. So we have responsibility for that as well. So not just the strong thunderstorm wind and hail, but also the hydrologic aspect. We do a lot of data collection activities. Obviously, the balloon launch, we measure rainfall. You have these automated observing systems that we're responsible for the maintenance of that record variables like temperature, air pressure, dew point, wind speed, etc. There's also, although we're not necessarily responsible for them at the local level, there's things like the National Data Buoy Center, which is responsible for buoys. There's actually seismic sensors and tsunami sensors, so a lot of observational sensors, and then obviously the radar and several satellites. We have satellites both in low Earth orbit and geostationary, various weather satellites. A lot of you are probably familiar with the GOES satellites, that series of geostationary satellites, all basically the National Weather Service in collaboration with other NOAA line offices are responsible for all that, the development, the maintenance, etc. We also provide public forecasts, which is something we call the National Digital Forecast Database, or NDFD. We produce these a couple times a day routinely of a variety of elements. And that's where if you go to like our website, you'll see what we call the point and click, which is data like this. We also have hourly weather viewers that come in a variety of flavors, the old school time series on the right, and then the newer format, which is known as the IDSS forecast points, which I actually prefer a lot better. We don't technically, I will point out, have an app, a mobile app. For whatever reason, our agency was very late to the game with that. We do have an app called Everything WX that was actually made by one of the forecasters of this office, which is probably the closest thing you can get to a true NWS app, because it uses all NWS data, including the forecast data. Whereas your other apps on your phone, your default iPhone, your Apple app and stuff, are going to use their own forecast, although they will still have our watches and warnings, because the Weather Service is the only agency that's authorized to issue watches and warnings. We also do a lot of marine and aviation stuff. We issue coastal waters forecasts. We issue all sorts of products for hazards. You've probably seen small craft advisories. We also do aviation forecasts, most notably what we call the TAFs, which are terminal aerodrome forecasts. So you don't get to use the word aerodrome a lot, but it is in the name for TAF. We basically provide pilots for at least major airports with what they can expect weather-wise over the next 24 hours. A lot of fire weather. Fire weather is very important. We issue obviously hazards. You guys have probably heard of things like red flag warnings for days in which we're expecting usually high winds, low relative humidity. We do a fire weather planning forecast. We also can look at fire starts on satellite. Actually, there's some algorithms that can kind of basically see heat signatures on satellite, which can help us alert authorities that there is a fire that has started before they even get notified. And then finally, there's a segment of NWS forecasters or meteorologists that are known as incident meteorologists or IMETs that actually get deployed to work like on the site of a fire and basically coordinate with all of the firefighting crews, telling them all the latest details about the weather, because when it comes to fighting fires, things like wind shifts and lightning can be deadly. I mean, there's been incidents where an unexpected shift in winds behind a thunderstorm causes the fire to basically start spreading in the opposite direction, and it threatens the entire operation. There's been, unfortunately, wildland firefighter fatalities in the past. So these IMEDs are really vital, and they do very important work. Also, not just for wildfires, but also for like hazmat incidents, we do these things called high splits, which basically we do these plumes of, like, say, a chemical release. You get information on like what type of chemical it is, and then obviously you tap into the atmospheric models that have the winds at different directions, and will show kind of where this plume is expected to go over the next X hours. And so this is something that luckily we don't have to do on a routine basis, but occasionally you do get that call that, oh, there's been a chemical release, there's been an accident, we think something's being released into the atmosphere. Where is it going to go? And are we going to have to make evacuations for local communities? We do a lot of public education and preparedness. On average, we have 100 public speaking engagements per year. That's a little more limited than usual, given we're a little bit restricted at the moment from what we can do. But we still, at least in major conferences, we give a lot of things like that. We also do a lot of local drills and exercises. Often they'll be called tabletops with emergency officials. We make these briefings to core partners, both routine and for significant weather events. Like, for example, a routine example is this Coast Guard briefing we do every Monday. Here is the one we actually did from last week. We do this drought briefing also every Monday. Unfortunately, with the pattern we've been in, that's been probably our most interesting briefing, just because everyone wants to know when will we actually get rain in this area. And then for big events, like obviously for Hurricane Beryl, we make these kind of longer briefings that we disseminate to our partners. And then we do on-site support as well. I was talking about those incident meteorologists that go to fires and things like that. For big events, we actually will go be embedded. We'll have at least one forecaster be embedded within local emergency management. In this case, for Beryl last year, one of our forecasters was embedded in the Victoria Office of Emergency Management, kind of just so they always have someone they can bounce weather questions off. Like, what is the timing looking like? Has things changed? Has Beryl forecast to now go more to the northeast, which it ended up doing, which kind of spared most of our area. But it helps when you don't have to have that, when you don't have any lag between what the weather information coming out and the actions that the emergency managers take. We also produce a lot of graphics that kind of go along with everything I've just mentioned. We put stuff for our website. We do social media, Facebook and X, and things like that. So we produce a lot of graphics of various formats. We also do local research, which is something me as the science and operations officer, I've done a lot in my career. I just have a bunch of random samples of studies I've done in my career, from random forest for fog prediction and neural network for wind gust forecasting, an observation study comparing a variable called Whipple globe and heat index, making probabilistic predictions of gust factors for tropical cyclones. So something I enjoy doing a lot, but it's also something we do at a local level because, yes, there is a national kind of science effort being undertaken in the NWS, but sometimes for very local effects, like if you have fog, wind gusts, things like that, that are a more local level, the local office has the responsibility to do these kind of studies. And this leans into kind of as we get to the main point of the talk, which is that we have a long history at this office of collaboration with you guys, particularly the CBI. Over the years, Dr. Tissot's group has been a big help with some of our main forecast problems. A lot of you are probably familiar with the cold stunning model, or the temperatures of the Laguna Madre forecast model. There's some other endeavors. There's recently a fog prediction algorithm that went live. There's kind of the tidal prediction algorithm, which is another one of the more classic ones that's been going on for a while. There's new studies for like Oso Creek, combined freshwater tidal flooding. So really good history between our local office and TAMUCC. And this is something that's important in general in the Weather Service. A lot of you guys probably have heard the term, the buzzword R2O, research to operations. We're doing the operations. We're getting stuff out often to the public, to emergency managers. And we don't have usually the bandwidth or the resources to carry out some of these, what I'd consider more involved research studies, which is something that academia is really good at, and so it is really a good collaborative environment, I think, between the NWS as a whole and then this office in particular with academia. Okay, so now to some of the research projects. So our office came up with basically 3 potential research projects that, depending on if there's interest, any one of the 3, we'd be fine to help with the project design, the data acquisition, things like that. But let's start with the first one. So the first one I'm titling, "Where have the summer thunderstorms gone?" So the background is that we in South Texas receive most of our radar in what's known as the warm season, roughly May through October. And you see here in all the graphs for all these sites that the bulk of the average rainfall occurs kind of between May and October. Now, there are a few mechanisms that create this rainfall, basically. There are, in the late and early season, we actually, kind of in May and October, we still have frontal passages. We still have these upper level systems that come in from the west that do cause rain. We may have one actually later this week into this weekend that kind of fits that mold. We also obviously have occasional tropical cyclones, which, although they're infrequent, can produce very large amounts of rainfall. I mean, you could easily get double-digit inches of rainfall from a tropical system, but they're infrequent. You won't get them every year, certainly not every month, hopefully not every year, and hopefully not every month. So the main mechanism is actually the sea breeze, which is very reliable. Most of you probably anyone that has a background in meteorology or even has lived along the coast for a long time kind of know how the sea breeze works. In the summer, the land tends to be warmer during the day than the water. So you end up getting what's known as a thermal low over the land, which essentially draws air, which draws air from the sea. So you get a wind flow from the ocean to the land at the low levels, and then it reverses when you get a little bit higher up. But basically, this influx of moist air, so it's air that is kind of primed to precipitate, and then B, you just kind of get this convergence of air over the land. And if conditions are right, this convergence will create rising motion, which will create clouds. And then if conditions are right aloft, these clouds can grow into the cumulonimbus clouds, which form the thunderstorms that we so know and love. But now, anecdotally, many forecasts at this office and then also even at the Houston office believe that the frequency of this warm season sea breeze driven rainfall has decreased over recent years. If this assertion is true, this would make our rainfall more dependent on those infrequent tropical systems, which results in potential for longer periods of drought and more interannual precipitation variability. Or, kind of in other words, our average rainfall could vary considerably more because we wouldn't have these reliable sea breeze thunderstorms. We'd have to be like, okay, did we get a tropical system this year that dropped 15 inches of rain? Oh, if we didn't, then our drought that usually, and like I said, we're usually not going to really help our drought much in the winter because we just don't get a lot of rain in the winter on average. So we really rely on these warm season months. Furthermore, there's actually other effects than just the rainfall. There is aviation forecasts, like, are we able to predict like clockwork that, okay, at this time of the day, thunderstorms are going to develop. So therefore, if you're a pilot, you should know, okay, avoid the airports, carry extra fuel because you may have to divert. And then there's also the heat risk aspect, because usually the sea breeze is one of the things that actually will help cool you off. If you get thunderstorms that develop, you get clouds, you get precipitation, you get outflow, and all that stuff helps cool you off. If the sea breeze just comes in and doesn't really develop any thunderstorms, you're just getting hot and humid air usually, kind of coming in. So the sea breeze doesn't actually have much of a cooling effect, and this actually increases the risk of heat related illnesses. So here's just an example of sea breeze thunderstorms in Florida. In Florida, it is like clockwork. I worked at the Miami office for several years. And if any of you guys have ever been on vacation, lived in Florida, went to Orlando Disney World, in the summer, basically between about the months of like June and September, you can set your watch to the timing of the thunderstorms, at least based on what direction the low level winds are coming from. In Texas, as we kind of anecdotally see, it's a little less like clockwork. So here's a lot of text in this slide. I apologize. But so there's a couple of questions that can be answered with this project. The first thing would be, is this anecdotal kind of assumption that the sea breeze frequency of sea breeze thunderstorms is decreasing? Is that actually true? So if we looked at like the last decade versus like the previous maybe 2 decades, you could answer that. If they are decreases, kind of go into a little bit like, why is it happening? There's a few theories. There's kind of the thing that, okay, the water has been getting warmer. So therefore, you're not getting as much of a contrast in temperatures. Therefore, your sea breezes tend to be weaker. There's also kind of an atmospheric reason, which is that we kind of get this, some of you may know it as the death ridge, the heat dome, this mid-level ridge that forms typically over the southern plains, especially in the months of like July and August. And is this feature, is it actually the case that the land is warming up greater, so this ridge actually is stronger, so you get this sinking motion, which like basically cancels out the rising motion you would get with the sea breeze? And then finally, the kind of the forecast aspect, which has more of the machine learning as I would see it. Since these sea breeze thunderstorms are getting harder to predict, and a lot of the high-res models that we have, these so-called convective allowing models, they actually don't do a very good job. They'll often will either forecast sea breeze convection when there is none, or they'll forecast none to develop, and then you do end up getting thunderstorms developing. So could a machine learning approach do better than these dynamical models? Could you develop a model that basically gives a probability possibly at various sites along the coast, because on a given kind of sea breeze day, not everywhere along the coast has the same chance of getting thunderstorms, depending on the orientation of the coastline, the orientation of the winds, other atmospheric parameters. So could you give us something that would give you at least like a 12-ish hour lead time, something you could maybe run in the morning, that would give you the probability of thunderstorm development in the afternoon? The data sets that I'd see for this one is obviously, for the observational standpoint, you would need something to determine whether the sea breeze occurred on a given day. I mean, most days in the summer, the sea breeze does occur. There aren't a lot of strong, what we call synoptic systems that would prevent the sea breeze from occurring. And then also how far inland it pushes. This is something that does vary. Some days the sea breeze can push all the way to almost Laredo, whereas other days it gets pinned and gets stuck closer to, say, Corpus Christi Airport. This is pretty easy to determine. There's lots of point data that have at least 25, 30-year periods of record, and you could easily make some kind of an algorithm that looks for when the winds go a certain direction and get a certain speed and you get a certain increase in humidity. I've done this actually before in previous studies, so I have a pretty good idea of how this could be done. There's a more complicated way, which is where you often see breezes, even when they don't produce clouds, have what's known as a radar fine line, which is often bugs that basically get pushed inland by the sea breeze, and the radar actually detects these bugs. And then on satellite, even if there aren't thunderstorms, you'll often see a satellite cumulus line, which is more the shallow cumulus that you'll see some days. But this is a little more complicated. The satellite and radar data, although certainly some of you are familiar with it and exists, to make an automated algorithm of this is you're going to more image processing, which is a little more difficult than this other thing, which would be more just data time series processing. And then finally, you need to determine how widespread was the rainfall that actually occurred in these days. There are stage 4 and MORMS are two rainfall data sources that are gridded, so that's useful because you can kind of see everywhere. But they have limited historical. This says variability, but I should say a limited historical period of record, especially MORMS, which is only really in the last decade. So this could be a challenge. Stage 4, which is the kind of the official NWS rainfall estimates, does go back further. You could just look at point observational sites that do have a longer period of record, but obviously if you have point measurements, it can be a little more tricky to parse out like how widespread rain was everywhere. And then finally, atmospheric and oceanic parameters to determine why is something changed as the strength of this 500 millibar rain ridge changed over the years. ERA reanalysis is a good source for that. And then for the probabilistic, for actual model, you would want to have forecast data from a model such as the RAP or the HER to use as training data to actually as the inputs to your model to predict whether sea breeze would occur. So that's project 1. That was a mouthful. Project 2 is a little more straightforward. This is a problem we often have in the winter, in the cool season. Between November and March, we often have these stratus clouds which have bases below 3,000 feet, occasionally even below 1,000 feet, that are pretty common over South Texas. Because what happens is we get usually either cool air from the Gulf shelf waters, or occasionally we get this Arctic front that comes down from the northwest, and you get this very shallow layer of cold air. And then you get warmer air above that. And warmer air, as a lot of you know, warm air rises. So if you have warm air on top of colder air, this is an inversion of the usual way temperature works in the atmosphere. Temperature usually decreases as you go higher in the atmosphere. Whereas when you get this situation, this inversion situation, you essentially have a lid and you get all that moisture at the low levels trapped below that lid. And so you end up getting these clouds form, these low clouds form. And as you see from this graph here, this bar graph series, this basically shows the amount of time, the percent of time that we have clouds that are below 3,000 feet. As you see, as we go to the summer, it doesn't happen very often. If you look at this green bar, for example, between like June and October, it's less than about 10% of the time. Whereas in January, February, December, November, it's like 20 to 30%. So it's much more of a cool season event. As we get to this time of year, eventually the sun is a little stronger, so it tends to be able to warm the surface. It tends to be able to kind of evaporate these clouds out as day progresses. Like even a day like today, actually, we're starting off with the stratus clouds, which eventually is going to gradually kind of clear up, increase in height and things like that. But if this was happening 2 months ago, it's possible these low clouds would last all day. So the current suite of guidance that we have does handle kind of this morning overnight stratus pretty well, at least compared to how it used to. But it doesn't handle well when this cloud deck is going to finally move out, basically. It'll say, okay, the cloud deck's going to clear at noon. The cloud deck doesn't clear at noon. It stays in place the entire day. And like you see the satellite imagery from January, this was at like 19Z. It's 19Z in the winter. If I remember right, it's almost like mid-afternoon. We're talking like 1, 2 p.m. So usually stratus is kind of clearing out by then, but in the winter, often it won't. And the problem with this is our temperature forecast can bust very dramatically, even our short term. Like look at this day in February of this year. This middle panel is what we forecast the temperatures to be. And this was the forecast the previous night. So we're talking about a forecast of only a 12-hour lead time. We should be pretty good at those, right? You would think only a half a day lead time forecast. We forecasted highs in the low 80s. The actual highs were in the 60s and 70s, and our error, which is this thing on the right here, you see a 10, 13, 14 degree forecast high temperature error, which is quite bad because typically in the cool season, our average error is like 3 degrees for a forecast at this time series. So if you talk about the difference between a 14-degree error and a 3-degree error. So these stratus days where they never lift, they just stay the whole day, and guidance is out to lunch is a challenge. And that's also aviation purposes. As you imagine, aviators usually don't like flying when there's low clouds. So often in our aviation forecast, we'll say, okay, the clouds will probably dissipate or lift at around 18Z or around noon. And then they just don't lift. And we're just coming to hats constantly backtrack and say, okay, now they're going to lift. And then some days with the opposite. We think the clouds will never lift. And we do a cool forecast, and the clouds do lift, and our temperature busts the opposite direction. It's much warmer than we expect. So that this one's more simple. Produce a model that can improve the short term, and we say short term, I would say about like a 12 to 24-hour lead time of the low stratus duration. When is it going to break up? And also possibly how low the height will be. Is it going to be like a 1,000-foot deck or a 3,000-foot deck? Because this is important for aviation purposes especially. And then also, we like kind of like explainable AI is not exactly what I mean by this, because that's a whole separate thing, as some of you know. Some way to actually determine which predictors are actually most important for this, because a lot of our forecasters don't like the idea of black box machine learning models where you have an output, you have no idea, okay, why was this day the output this, why was this day the output that. We often like to have somewhat of an idea of what predictors, what combination of predictors are very impactful to this. So this would be useful with this model, and also with the Seabreeze model as well, I should add. This would be pretty easy in terms of observational data sets. We're a lot of worried about aviation, so you'd actually could probably just use the point stuff. You could use the satellite imagery. As we saw from the last thing, you could look for days in which you have certain parameters and certain satellite bands, but this would be more complicated. And then finally, like similar to the other one, model data set for atmospheric inputs. Because this one would be mostly atmospheric inputs. Maybe you could have some oceanic inputs due to the influence of the shelf waters and onshore flow, but not sure. Finally, the third project, this is basically do thunderstorms, which initiate along the higher terrain of northeastern Mexico. Basically, as many of you know, there's mountain ranges in northeastern Mexico. La Sierra Madre Oriental is one of the more prominent ones, and often you'll get thunderstorms that will initiate along the higher terrain in the warm season. What's happened a lot last week, especially when you have what we call upslope flow or flow out of the southeast. And then these thunderstorms, though, whether they propagate off the terrain and actually impact our area is kind of uncertain. This is a run from the HER, which is one of the top high-resolution models. You'll see these thunderstorms develop over the higher terrain, and then the HER just kind of dissipates them. It says, okay, they develop over the higher terrain, and then as soon as they try to propagate towards the valley, towards the Rio Grande, towards the international border, they die. What actually happened that day? So this is actual radar. So you see the thunderstorms developing along the higher terrain, just as the HER was saying. You see, okay, it looks like, okay, they're dying. Yeah, the HER was right, wasn't it? But no, you get this redevelopment over the valley where you actually get a splitting supercell in the early evening. So the HER was dead wrong. So if you're trying to forecast, if someone asks you, hey, what is it going to be? Is it going to reach Laredo or Webb County? And you say, nah, doesn't look like they're going to survive today. But then what do you know? A couple hours later, you get a severe thunderstorm that produces 2-inch hail and several inches of rainfall. So these are not forecast well by current convective allowing models. So the research question is, produce a model which can basically do a better job of determining whether storms will survive to reach the Rio Grande Plains, especially the Laredo area, because that's where you have a few 100,000 people. There aren't quite as many people in other areas. And then similar to the stratus question, give us what atmospheric parameters. Is it the flow aloft, the stronger winds aloft? Is it an instability related? Do you need a certain level of instability in the valley to kind of keep these storms surviving as they go off the terrain? And then obviously you have observational data sets. Probably your radar, you're going to obviously need to use radar in this one, which can be a little tedious because you're actually going to have to probably get radar data from the AWS is actually where most of the NextRad data is stored. So if you're familiar with how to use like Amazon Web Services, how to get data from that. A big thing is actually looking, we get a lot of severe thunderstorms from this, like we had last week. A lot of the storms end up being severe. So you can even look at our archive warnings, which are pretty easy to get. And also MRMS for precip. We wouldn't need as long of a data set as for, say, the sea breeze stuff. So I think really MRMS would work for this. You only need a few years of data. And then obviously you're going to want a model data set for the atmospheric data that you would use to train your model. And finally, I have two other projects that would be very difficult, but maybe you guys are smarter than me in some of these areas, so you could think about how to do them. The main reason these are difficult is because for any machine learning model, as you guys know, usually for a supervised model, at least, you need a verification data set to train the model with. Unfortunately, these phenomenon, although they're very impactful, especially rip currents are real impactful, there isn't a good verification data set because most people just don't go out and get caught in rip currents. So our current way we forecast rip current is pretty bad, to be honest. I don't think it has much skill. Machine learning has been used actually in the study I listed this citation for, but they actually had cameras on the beach. They would actually use cameras and image processing to determine if a rip current occurred, and then use that as the training verification of their model. And then they used their input parameters, I think, were like wave period, where it was in the tide cycle, wave height, wind direction relative to the shore, things like that. The issue is we just don't have as good a verification data set here. We have some lifeguard data. We have some data from beach patrols and like the number of rescues they have in a given day. But we don't have, I think, a robust enough verification data set. But this is a good problem. If some of you guys have great ideas for how to do rip currents, this would be a very worthwhile. One thing that is less impactful, but we do get a lot of phone calls about it and social media responses, are these things called tropical funnels, which occur a lot of times in the warm season. These often don't reach the ground. That's why they're not super impactful, but occasionally they do become water spouts. These funnels are formed by non-supercell processes. They're non-tornadic. So their mechanisms for formation are much more nuanced than like a supercell thunderstorm, which we have a good idea of how those form. These ones, though, they're very random, and occasionally, like I said, they can cause a lot of buzz. People on vacation, you'll go to the beach, they see this stuff, and all of a sudden our phones light up like, oh my goodness, there's a water spout, there's all this stuff, and we don't really have a good way to predict them. Now, Key West and the Florida Keys, where they get a lot of these, had actually a statistically based study, but they had a lot more verification. I don't think we have enough verification to actually do a study on this, but if any of you have any ideas, also similar to the rip current thing, I'm open to them. And that, I apologize for talking your ear off for the last 45 minutes or so, but those are my main ideas I would have for a research project that we could collaborate with if any of you are interested in taking on one of those challenges. But let me know if you have any questions about any of the stuff or if you have any other ideas, and I will give the floor to you guys now.
Thank you, Nick. Are there any questions in the room?
Okay, I see Philippe has a question in chat. Famous corporate. Oh yeah, yep. He's talking about Robert Simpson, and then for the operational machine learning predictions of sea breeze, which high res we think would work best. I would say probably for a lot of these modeling things, the HER tends to be the best with convective initiation. There is actually, unfortunately, there is a kind of a new model that's debuting this summer that theoretically would be good, called the RFS or the Rufus, but there just wouldn't be a data set for that. So the HER would be my model of choice. The NAM Nest or the NAM 3K is another option. Interestingly, for the Stratus problem, I actually think the RAP would be a good model because the RAP has a little less noise than the HER when it comes to especially clouds, in my opinion. But for the thunderstorm project, the HER would make the most sense. I think it would probably be the best input data set.
Hello. Um, Thank you so much, Nick. I can tell you really put a lot of effort into this presentation. I really appreciate how thorough you were with presenting the projects. I did have a question about the one called Where the Sun, or Will the Sun Come Out? This is not my area of expertise, so I was following along for the most part, but this project, I was a little confused. And I was wondering if you could maybe put in a little bit simpler terms about how is it the cloud cover that you're measuring to see if the sun will come, like how much are we measuring, like the cloud cover, or how much the sun is, like, I don't know, like how much reflection it's getting? I don't know. I was a little confused. Thank you.
Yes, no, good question. Actually, interestingly, you brought that up. I kind of got a second idea. You could actually use some of our sensors actually have radiation. You could actually use to see the stratus, how dense it is. But basically, this project would be: is this cloud deck, this stratus deck, going to break up today? Are we going to see the sun, or is it going to be cloudy all day with these low clouds? Because the models we currently have don't do a good job predicting whether these clouds will last all day or whether they're going to break up in the afternoon. And that, like I said, has effects on our temperature forecast. If the clouds don't break up, it'll almost certainly be cooler than a lot of the guidance forecasts, because a lot of the guidance, the models we use to make these forecasts, they'll say, oh yeah, the clouds will clear up. It'll be sunny by the afternoon. So they give us high temperatures in the 80s. And if the clouds don't clear up, temperatures may only be in the 60s. So that's the gist of this project. Do a better job than the current guidance in whether these clouds, which are stratus clouds, will actually break up and we actually during the day, or if they're going to stick around all day, basically. Hope that answers your question.
Okay, this is Mohammed, and I have a follow-up question regarding this. So what type of data set are you using for this, like Sentinel data?
So you mean like to determine whether or not the clouds did persist through the day?
Yes.
There are a few ways you could do this. You could use we have our geostationary satellite here. There is a visible band, so you could use that data. An easy way though, we have a decent amount of observation sites that actually record the cloud. They record A, the radiation, or B, they record the actual cloud cover. And you could just even use those point sites and do a little bit of interpolation, and you'd probably be able to get a representative picture without even having to use a satellite data set. So I think you could actually do even easier than that. You can just look at these observations that record, okay, here's the clouds it's currently overcast with a 2,000-foot ceiling. You could see that every 5 minutes, and you can say, okay, well, today that overcast 2,000-foot ceiling lasted the whole day, whereas in this day it broke up at 2 p.m. So what's the difference between the day it broke up at 2 p.m. and the day it lasted all day? And that's one of the big things from this project, would be determining if there's a signal in this data for better predicting when this data would break up.
Other question, after flood or storm event, do you guys also map flood area after these events?
Yes, that's a good question. Satellite flood mapping is something that's becoming much more used, especially after tropical systems, your hurricanes and things like that, especially when there's any kind of tidal component, when there's like storm surge and things like that. There's a whole another kind of area called flood inundation mapping, which I didn't technically include in the hydro thing, but is becoming very, very much a thing we do, where we actually do try to forecast like the extent of not just, okay, this river is going to go into flood, but exactly how deep is the water? What structure is going to flood? Is this building I have located right next to the river? Am I going to have water in my parking lot and things like that? So that's another aspect. And then in terms of the observational thing, like after the fact, we at the local office don't do this as much, but some of the NOAA satellite branches do that actual mapping based on satellite imagery. I think synthetic aperture radar, SAR data is big for that. I'm definitely not a subject matter expert on that. And then the other thing I was going to say was I did forget to mention in the stuff we do, we actually kind of going into that vein, we do the damage surveys after tornadoes, especially, but any kind of big severe event. We're the ones that do the classification. We look at the damage and determine, well, was that tornado an EF1, EF2, EF3? And we actually do use satellite occasionally for that because you can see often vegetation scars in some of your vegetation index-based satellite data from when tornadoes go through, especially forested regions where there aren't any people to give us reports. And yeah, I see. And so that's another thing we do that I forgot to actually mention in the, it's actually a pretty important duty we do because we do get a lot of feedback, like how strong was that tornado? So hopefully that answers some of your questions.
Hi, Nick. This is Delaney. I appreciate your talk today. Really great problems, really awesome research opportunities. As an atmospheric science, this is really interesting. My main question, though, as you mentioned the Amazon data acquisition, can you be a little bit more specific on where the location for the data sets that you were suggesting would be at so that we can kind of get a gist of where they're at and how complicated it is to access those?
Yes. So the radar data is in an Amazon bucket, S3, I think. We've had to use those in studies in the past. So I think I have some scripts that actually will pull radar data from those buckets. So if you need any help with that I know relatively well. The observational data also very easy. I've done that in the past too. For certain sensors, you have to use something called IEM-COW, which is Iowa State Mesonet, has a lot of great easy APIs that you can pull data. There's also Synoptic API, WeatherFlow, these other data networks that are even bigger than the ASOS data that I've also used before. So I'm actually pretty familiar with the observational data. The satellite data I'm less familiar with, so that would be something I would have to probably ask someone else that has pulled. So if we were going to use satellite data, for example, for one of these this cloud study, for example, that I would probably have to do some research myself on how easy. I know there is archive data for that. It's a little more complex. MRMS, I know Philippe has used that before. I've also used that before. Relatively straightforward to pull that data as well. Also the stage 4, that rainfall data I mentioned, I've used that in the past for studies. The only complexity with that is they used to use a very weird coordinate system called the HRAP, which is a very weird projection, I should say, that made that a little complicated, that I'd have to familiarize. If anyone wanted to use that, mostly for the sea breeze study, because that's a precipitation data set. But yes, the observational data set for like, okay, what was the clouds like this day? When did the sea breeze come through? That's pretty easy. The radar data, like I said, at least the NextRad data that you'd use, fairly easy. Satellite a little trickier, but I'm sure someone would be able to figure that out because it is free, it is available. I know that.
Nick, this is Audrey. I believe when you were going over what the service does or can do at the beginning, you mentioned that you guys have helped predict or forecast when contaminant releases into the atmosphere, where they're going to go. So Ingleside on the Bay Coastal Watch Association kicked off our mini workshop series, and their research questions relate to air quality from Portland to Ingleside on the Bay. Is that a potential project that you guys would be able to assist with?
Yeah, so air quality is an interesting you bring that up. So weirdly enough, some NWS offices do in fact issue these air quality alerts, these AQIs and stuff, and this product called an AQI. Although weirdly, we're usually told to issue that by the EPA. So really, we're the. Oops, sorry, I'm going on a thing, the Air Now thing. I forgot that I was sharing this entire window and not just the tab, but yeah. So in terms of air quality itself, we're usually it's kind of we're told to issue something. We don't do the actual modeling that does the air quality stuff. Although typically we kind of have an idea of on a given day if it's going to be a bad air quality day, just because we know kind of the atmospheric profile? Are you going to have a lot of dispersion? Are things going to actually be able to rise and disperse, or are they going to kind of be, or are they going to kind of be close to the surface? Occasionally, you'll have fires where you get smoke and particulates that go from fires that are far away but get transported by the winds in the upper atmosphere. So we don't directly do the air quality forecasting. That's an EPA thing. But we can sometimes have an idea of like if it's going to be a bad or good air quality day, just knowing how the atmosphere parameters are, especially if it's a fire related. The NWS actually has some smoke modeling that we do that also can kind of, especially from like distant fires. That was a big issue when I was when I worked at the Philadelphia office. We'd weirdly enough get these fires from fires in Western Canada that would travel all the way to our area, and you'd get these vivid sunsets and things like that. And people would always be asking, what's going on? There was a day that New York City, some of you guys may remember, where it looked like it had a very crazy hue to it, and that creates a lot of attention too. So we do some of that stuff, but in terms of direct, like your AQI, your air quality index, which is the main thing, your particulates, your PM, X of X compound, the EPA is mostly responsible for that.
Hey Nick, this is Chantal, and I'm a professor here and atmosphere scientist. So thank you for presenting all these great problems to have. And for the cloud cover problem, I think we probably want to zoom into a specific location because that area probably vary from one site to another. Closer to Corpus Christi, close to the sea breezes, and of course, in the wintertime, the sea breezes are not really there, but summertime sea breezes are really strong. And so, three questions, three problems. Which one do you think has most data available? Relatively easier to access.
Yeah. So I mean I think this cloud one and the Mexican plateau thunderstorm one, I pretty much know. I would have a good idea of like basically how to do both of these projects, like a general project outline, and also where to get the data. The Seabreeze one is, I think, a more robust project in some ways because I think it is a real question that I do think would be very interesting, but it's more complicated because you have to first make an algorithm that determines basically the sea breeze inland extent, and then you also got to determine like thunderstorm coverage. Technically, you also should probably determine whether the thunderstorm coverage was related to the sea breeze or not, which in the kind of like May and October and stuff, it's not always straightforward. It's easy to tell if it was a tropical system. Tropical systems, they get names. We issue products for them. You could easily filter those events out of the data set. Frontal systems, you'd actually have to look at like the upper level pattern and things like that. That'd be a little tougher. I think this project would be beefy. It's doable though, I think, but it is very interesting. These other projects I think are more straightforward. It's certainly impactful. Like I said, there are things that the current guidance we have doesn't do well. So I think you could actually make a model that improves upon guidance, which everyone at this office would be very thankful for, to have better guidance. That's what a lot of Philippe's stuff, his group, has been doing, like our tidal guidance, fog guidance, things like that just are not the current numerical modeling suite just isn't very good just yet, and maybe they never will be. Who knows? we hope they will. So I didn't want to step on any of their group's projects. Like some of their projects, like as I mentioned earlier, fit in the same vein. These are tough problems for us. So I wanted to think of some new things that they weren't already doing, basically, to try to get some more coverage. But I think these two, the radar and the Stratus problem, are fairly straightforward. Yes, getting the radar data and actually analyzing it. Getting the radar data isn't hard, but actually analyzing it, you have to make some routines to analyze the radar data. That would take a little bit, There actually are, if you use Python, some modules that are really designed to work with this kind of radar data, this so-called level 2 radar data. So you wouldn't have to reinvent the wheel, but you may have to reinvent the wheel a little bit in how you analyze kind of the spatial extent. Like, what is considered convection getting off of the plateau? How far east does it have to go for us to consider this a day where the convection survived into Texas? Do we say it has to reach across the border? Do you have to have precipitation observed in Texas versus Mexico, et cetera? That's all stuff you'd have to work out, I think, in the framework of the project. But this first project, it would be trickier. It would be more work, but I do think it would be very interesting. So that's kind of my spiel on the three ideas. And then there's also these ideas too. But as Dr. Tissot said in the comments, rip currents, unfortunately, it's a problem that would be great if we had a better verification data set, because it's low hanging fruit, because we're currently so bad at it that you wouldn't have to make a very good model to be better than what we currently are. But the problem is, I think it's hard to make a good model at all at this point. So that's my 2 cents on that.
Thank you, Nick. Great presentation. So our trainees from here on will be working on feasibility assessment for the projects that have been presented. And you'll receive an executive summary of their findings there. And then we have our big stakeholder workshop where we invite you all to come join us for the day on May 20th.
I just want to respond briefly to Philippe's thing. I was about to type it, but I might as well respond verbally. Yes, that's actually can be one of the big impacts. Even some of those days, I think you've noticed, where our temperature forecast, we recover too quickly, and that causes your water model to, in turn, kind of come out of the event too quickly. Sometimes this is the reason. Sometimes these stratus days, where it's, in this case, the temperatures being 80, and we have models that forecast a high of 60 and ends up being 48 or something like that, and that causes a big difference. So that's another big impactful thing. These stratus things can cause even downstream effects to, like, the water temperature cold stunning model, I think. So this can be an impactful thing. And often it occurs, like you said, days after the cold front, because you get that cold air mass at the surface that's just stubborn. It's very dense. It doesn't want to move out, and you get warm air kind of going above it and just get stuck below it. And models don't do a good job handling those shallow cold air masses. So yeah, so I just wanted to answer that, because that's another great reason why the stratus thing is also impactful as well.
Yeah, thanks, Nick. That's what we've added. That's the biggest weakness that we have in our cold stunning predictions. Is after that, and we made a hypothesis that this was the problem. We've also collected some radiation data, some relatively cheap hobo sensors that we've put in the Laguna Madre. So I think we have at least 2, if not 3 years of radiation data there. And yeah, anybody interested in that problem, or most of the problems that Nick has talked to, would be glad to help.
There you go. There's some more good data for not only, just like I said, the good thing about radiation data, it's not just the stratus, like, does it exist? It's how thick and how actually impactful is it at the surface, which is really the root of this problem. Because you could have days where it's cloudy, but the deck is kind of like semi-transparent, and you actually do get a good filtering of radiation. The temperatures go up decently, although a sensor may say, okay, today the stratus lasted all day, but it was kind of this thin stratus. Whereas you have other days where it's truly those gray days. We all know how it is in the winter. The day that's just kind of like you feel like you're just not getting a lot of light. More like Seattle, like you feel like you're in Seattle. And that's kind of these days that are the most impactful for us, are those Seattle days, basically.
Thanks for the presentation.
Thank you, Nick.
Thanks for having me.
And with that, we've reached the end of our workshop today. So have a good day.